Hey guys, today we're going to be talking a little bit about how to do a titration. Not only how to do a titration calculation, but also what that might look like in a lab setting and how we might actually do a titration if we were in a lab. So you should be coming off of just recently finishing this virtual lab where you went in and you looked at different substances. And for example, I've got hand soap here, and we kind of look at the difference between the different concentrations of the hydronium H3O plus and the hydroxide OH minus concentrations. You notice that as we kind of raise one of the sliders here, or lower one of the sliders, we see those concentrations actually go up. So in this case, every blue dot there represents an OH. And you notice that as I raise that H3O plus, those blue dots, that OH goes away, right? And you can actually see that OH minus concentration going down. So what we're going to focus on today is this process, this kind of equilibrium between the two. And we're also going to kind of look at what this word actually neutralization, what that actually means. So a neutralization reaction is where, just like you kind of saw in the previous video, it actually started, if you hit pause right at the start before I start moving the sliders, you see that when the ions of the acids and bases come together, and those H3 plus and OH ions are equal, they react, they come together, this H3O plus and this OH minus come together basically to make water, and then they also will result in a salt. So here's kind of an example of what that might look like if we were to take HCl and we add it to NaOH, so hydrochloric acid and sodium hydroxide. We're going to get, there's our water, our H and our OH are coming together to make that water in the neutralization process. And then here's kind of what's left over. You notice how we have a metal here, sodium, and that's going to pair with this nonmetal, chlorine, to give us that resulting salt. So this happens all the time. Here's another kind of example. If we take nitric acid and add it to potassium hydroxide, again, we always see that water as a result, and then there's going to be some byproduct, salt. So a titration is basically when we take either an acidic solution and add it really slowly to a basic solution, or the other way around, where we take a basic solution and add it to an acidic solution, and all of those ions, those in this case it could be hydroxide ions or it could be hydronium ions. Remember those dots that were kind of in that simulation get used up. So the point at which we reach this neutralization point also has another name. We call that the equivalence point. So our computer simulation would actually look like this. We actually have equal amounts of these H3O plus and OH minus ions, right? And you can see that there's equal amounts when we're at that equivalence point, and we know that we've actually reached neutralization. So basically the whole purpose of a titration is to determine the concentration of an acid or base. So we might take something that we know in order to find something that we don't know. If I want to know what is the pH of this unknown substance, I could do that using a titration. And if we were to do this in lab, what you see here is this woman here this is called a burette, and inside here she has either an acid or a base, and then she has either an acid or a base in this burette, and one or the other. If this is acid, this would have to be base, or vice versa. So what she's slowly doing here, she's slowly letting out that acid or base and letting it react down here in that Erlenmeyer flask. So that known concentration, so when we do this in lab, we usually put the base in the burette, right? So here's kind of a schematic of that picture before, where she has the base in that burette, and she's slowly releasing that base and letting it neutralize or cancel out this acid. So we actually have a couple ways of describing this known substance. We could call it a titrant, right? Because that's what's doing the titrating basically. Or we could, and a lot of times we'll call it the standard, right? So if this is our standard, we're going to be able to figure out what this unknown substance is. So if we were to go through and plot our data, what we would end up seeing is we'd see, and this is called a titration curve. We have pH here on the y, and then we also have the volume of the NaOH here on the x-axis. So as we're adding maybe our titrant here, we're adding some of that known, let's see, in this case it would be a base, to the acid. What we end up seeing is we see that it's becoming more basic, right? Those H3O plus ions get used up. They get used up, and then eventually we hit a point where they're equal, right? And we have equal amounts of that OH and H3O plus ions. So at that point, we know is our equivalence point. So in order to do a titration, we would need something called an indicator. If I take an acid and I just add it to a base or vice versa, an acid and a base are colorless. They don't, it would just look like I'm taking 2 glasses of water and combining them. There'd be no way to tell when I was at that neutralization point. So we use an indicator to help us kind of identify where that transition range is, when it actually, that pH is changing. So when we see that indicator change color, that's our endpoint. We're done with the titration. We know we've reached that equivalence point. We know that the amount of base and the amount of acid ions are the same. So in order to find that concentration, we're really looking for that change in color, and you'll see that in the virtual lab. So a couple of common indicators that we might use, we almost always exclusively use phenolphthalein in lab when we're kind of checking, because phenolphthalein is kind of on that line. You notice there's kind of a range here where we have, it's considered neutral. So we might use different indicators that have different transition ranges. So if I'm trying to figure out, well, okay, I know that it's an acidic solution, but you know, how acidic is it? Well, I might use thymol blue to determine, is it within that range of 1.2 to 2.8, and then I might do another one to kind of narrow that range down to actually figure out what that pH is. So here's a list of maybe some steps or a procedure for how to do a titration. Now, I'm not going to sit here and read these to you. If you want to pause the video and add these to your notebook, feel free to do that. You're going to actually experience that either in lab or via a virtual lab. So let's actually tackle a problem directly from your homework, actually. So if you would, pause the video, open up the assignment for titration calculations, and follow along with me. This is number 1 on that practice sheet. So I have in this corner some steps, and if it's helpful, pause the video, add those steps to your notes if you're kind of a steps person. So number 1, we're going to write a balanced chemical equation. Well, we have the equation, but you'll notice it's not balanced. So let's go ahead and let's do that first and foremost. So it looks like I've got 1 Na, 1 Na. It looks like I've got 1 Cl, 1 Cl. And then over here, it looks like I have 1 OH, and it looks like I'm missing actually a hydrogen. I got the 1 oxygen and 2 hydrogens there, but don't forget this little hydrogen over here as well. So 2 hydrogens, 1 oxygen, 1 oxygen. So this is actually already balanced. So I'm just going to fill in 1s here. And we'll clean this up a little bit. So number 2 says we're going to use the molarity equation, and we're going to determine the number of moles of the standard used. Again, the standard is what we know. That's our known solution. So let's take a look at the problem. So we've got a titration of 35 milliliters of drain cleaner solution containing sodium hydroxide. 50 milliliters of 0.4 molar. Okay, so we know the concentration of the HCl. And so that's going to be our known. So we're going to use the molarity equation to figure out how many moles is in that 0.4 molar HCl. So I'm going to take 0.40 molar HCl, and I know that that's equal to, remember our molarity equation is capital M equals moles over liters, all right? So I'm going to be solving for moles, and it doesn't say anything about liters. Oh wait, it does say 50 milliliters, but I need liters on the bottom here, so I need to change that. And if you remember how to do that, all we have to do is we get take that 50 milliliters, and we are going to divide it by 1,000. So when we do that, we're going to actually get 0.05 liters. Okay, so now I'm going to solve for moles. Now, if you remember from the molarity video, when we talked about this, the equation to solve for moles, if you can't do that, is going to be molarity times liters. So all I'm going to do is take this 0.4 times 0.05, and I get 0.02 moles of HCl. And so now we're on to step 3. So it says use the balanced equation to convert moles of our standard to moles of our unknown. Well, lucky for us, the equation really, if I highlight this, is a 1-to-1 ratio, right? So I'm trying to figure out this concentration of base. So what is my concentration of the NaOH? So let's just set it up, because it's not always going to be a 1-to-1. So let's still do the work here and show this. So for every 1 mole of HCl, and again, I'm getting that from the balanced equation, is going to be 1 mole of NaOH. So it's still going to be 0.02 moles, but what I did was I was able to change it from HCl into NaOH. So my last step here, we're almost there to the finish line, is we're going to use that molarity equation again, and we're going to calculate, well, okay, if we've got this many moles of NaOH, what's my concentration? Moles is not a concentration, molarity is. And back to the problem, if I'm dealing with 35 milliliters of that drain cleaner, that NaOH, right, that's going to tell me that I've got my 0.02 moles of NaOH. Again, gotta be in liters, right? So I'm going to divide that by, not milliliters, divide by 1,000, I'm going to get 0.035 liters. When I punch that into my calculator, I'm going to get a total of 0.57 molar NaOH, or if we are keeping in mind sig figs, 0.6 molar NaOH. So hopefully this video helped you out with some of the calculations, and if you have any more questions, feel free to ask your instructor. Thanks.